Hello everyone, this is Manohar Reddy, Department of Cybersecurity, Institute of Aeronautical Engineering College. Today I am going to discuss about the concept of syndrome decoding. Syndrome decoding. So the concept which occurs in coding theory. So the coding theory is a part of the correction of errors and identification of errors and recorrection of that errors, retransmission of the errors. So complete coding theory is going to tell about the theory of error correcting codes. So today we are going to discuss about the concept of syndrome decoding. Let me see how the syndrome decoding will works in coding theory. Right. So syndrome decoding is a process of identification of the errors. That is nothing but syndrome or nothing but semantics of the errors. That is nothing but symptoms that will occur in the transmission. So syndrome is a symptoms of that errors will occur in the possibility of the transmission media. Suppose H is a parity check matrix will take, so which contains the n comma k rows and columns. That is nothing but the matrix is always having the size of the rows and columns. So here the parity check matrix will have the rows and columns like n comma k code. Then for any vector v belongs to gf of q power n, that is nothing but Galois field of order n with q elements. Galois field of order n with the q elements in the vector. So here the formation to identify the symptoms of the errors, will have the formula is what? S equals to V H transpose. Here H is a parity check matrix. And V is the vector, input vector you can take. And here the S is the syndrome of this vector with the parity check matrix. So by using this formula, you can say that and you can identify that the symptoms will occur to detect the errors. So this form is called as syndrome of V. So S equals to VH transpose. So here V is nothing but vector and H transpose is nothing but parity check matrix, and S is the syndrome of this V. The syndrome of V is sometimes explicitly written as S of V. If you are taking as X, then you can write it as S of X. So it represents the syndrome of the vector, that represents the syndrome of vector, or symptoms that errors will occur at this vector. And it is called as syndrome. So S of V represents syndrome. So because it gives us the symptoms of the errors, thereby helping us to diagnose this error. So if you form this formula, then will identify the errors, then this formula is helping us to diagnose the error. So by using this formation of this error decoding or syndrome value, we are going to find the symptoms of errors that will occur. Right. So now we are going to see the two vectors having that syndrome, and that two vectors are going to find the errors or symptoms of that error. So see here, the two vectors you will take X and Y are in the same coset of C. Same coset of C is nothing but the same group of that code. So here C represents code words of that group, and this coset represents the number of elements or number of groups that will occur with the code words. So if and only if they have the same syndrome or not. This entire statement represents the group of the persons or group of the elements can have the symptoms that will occur error or not. So that is what we mention in this statement. So we'll see the proof. The vectors x and y will take and belongs to the same coset. The vectors x and y belongs to the same coset. That means x and y are the two elements or belongs to the same group we are taking, right? So well, coming to this code point of view, so x plus c equals to y plus c. We can write like this: x plus c equals to y plus c. So that x plus c and y plus c we can written as x minus y belongs to the c, because x comma y are same group or same coset. So that's why you can mention that x minus v belongs to c. So applying H transpose multiplication at both sides. So what will you get? So x minus y into H transpose equals to 0 into H transpose. So you can write it as x minus y H transpose equals to 0 into H transpose is nothing but 0. So like the way you can write, and simplify this x into H transpose minus y into H transpose equals to 0. And this expression you can written as x into H transpose equals to y into H transpose. And these two statements you can write as the formation of syndrome S equals to, the formation of the syndrome is what? S equals to V H transpose. This V is the vector which contains either x comma y. So that you can written as S equals to x H transpose, and that you can write as S of x. So this is what we written here. S of x is one syndrome and S of y is also one syndrome. So those two syndromes of the vectors will occur in the same group of the coset. So that will conclude that the two vectors in the same group will have the same symptoms. That is what we call it as same syndrome. Thus, there is a one-to-one correspondence between cosets and the syndromes. So group and the elements can have the same correspondence, one-to-one correspondence between cosets and the syndromes. That means groups and the group members that we'll mention here. We can reduce the size of the standard array by simply listening the syndromes of the corresponding coset leaders. So the group can have the elements and the group leader is nothing but coset leader here. So the group leader or coset leader contains the size of the matrix which contains both rows and columns. So by simplifying this all the statements, we can conclude that both members of the same group can have the same syndrome. So that is what we mentioned here. X and Y are in the same coset, that means same group of C, if and only if they have the same syndrome or same symptoms. So that is what we mentioned here, right? Well, coming to this, how the syndrome will occur and how the syndrome will transmission. The same symptoms are transmitted to one to another. So how will occur? So we'll see here. So we now extend the standard array discussed earlier by adding the syndrome column. So syndrome column we have to add in the standard array. So this is all standard array. For this all the standard array, we are adding a separate syndrome column. So see here, the standard array of code C is what? 0000, 1011 and 0101 and 1111. So this is the standard array of the codes to detect the symptoms of the same error, same group or not. So detecting the syndromes for the same group or not. So here we are adding an extra column, that is syndrome column. That syndrome column is nothing but 00, 11, 01, 10. You can add anything, like you can add 00, 01, 10 or 11. You can add anything. So this is what we added here, right? So see here how that symptoms will transfer to the next positions. We'll see. So first, in first vector, the 00. So where the 0 will occur, the 0 is transmitted as 1, and where the 1 will occur, the 1 is transmitted as 0. So see here, in this first point of view, the 0 is replaced as 1, and here 1 is replaced as 0, and here the 0 is replaced as 1, and here 1 is replaced as 0. That means the 1 bit movement they are occurring, the symptoms will occur. So we are going to change that symptoms to the next level. So for the next one, double one, so see here, we need to replace the 2 points. We need to replace the 2 points. The 2 points are nothing but first 2 bits. So see here, the 1 is represented with the 0, and this 0 is represented with 1, and remaining 2 bits are left. And similarly here also, the 0 is replaced as 1, and here the 0 is replaced as 1, and the remaining bits are left. And similarly here 1 is replaced as 0, and the other 1 is replaced as 0. So those two are left. And here also 0 is replaced as 1, and here 1 is replaced as 0. That means the symptoms are transmitted to the next level with the help of this syndrome, adding syndrome bits. So when this person is going to introduce with this person, then automatically the symptoms will transfer to the next person, right? So the same way here the bits will happening here. And similarly this pointer, so 0, 1, 0, 0, for this moment, so we are going to change the second and third positions. That means the second and third persons, how they are got affected. So see here, the 1 is replaced with 0, and 0 is replaced with 1. And similarly 1 is replaced with 0, and 1 is replaced with 0. And see here, 0 is replaced with 1, and 0 is also replaced with 1. And similarly here the 0 is replaced with 1, and 1 is replaced with 0. So all the bits were changed because of syndromes will occur, because of same symptoms will occur in the same group. So these are all having the same group elements, and among this all the same group elements, this is the Coset leader. This is the Coset leader. That means one of the highest member, one of the group member that leads to this all the elements. So that will we see here. So like the way the symptoms will transfer to the next bit positions or next persons. So the final person is going to be, you can conclude it as Coset leader. Coset leader. So this is the way you can say that syndromes will happening, and the syndromes will affect it to the next bits or next sequence. So this is the way you can understand the syndrome process. Next we'll see the syndrome decoding. So syndrome decoding. So the process of decoding is nothing but decrypting of the message or decrypting of the codes. So we already know that. So to decoding that syndrome, first of all we need to identify the syndromes are occurred or not. That means symptoms will occur or not. So identify the syndrome with the help of the formula S equals to VH transpose. So here the H is nothing but parity check matrix, as we discussed in the previous one, and S is nothing but syndrome of the vector. That vector represents V here. That vector may be V equals to X comma Y, you can take. So if you can say that S of X is nothing but the syndrome is respected to the X vector, and S of Y means the syndrome is respected with the vector Y. So like the way you can identify this syndrome first. To decoding the syndrome, we have to identify the syndrome first. So that of the received word is V automatically. So to decoding that syndrome, what we need to do? So locate the syndrome in the syndrome column first. In the previous session only, we added this one. So first we need to identify the syndrome by adding syndrome column. So that is what we added here. So we added the syndrome column, and next determine the corresponding Coset leader. So we have to identify the corresponding Coset leader. Also we identified here. And next what we need to do, so this is the error vector E. We need to identify the error vector E. So after finding that error vector, after finding this Coset leader, after finding this syndrome column, we need to do the decoding of the syndrome by using this formation. So that formation is nothing but, see, subtract this error vector from the received word to get the code word. So the code word is what here? Y. So Y is the code word. So Y is the code word. To get the code word, what we need to do? We need to subtract this error vector from the received word. So that is nothing but V equals to V minus E. That you can written as Y equals to, for the X vector you can write it as X minus E, or for the Y vector you can write it as a Y minus E. So like the way you can decode the syndrome. So to decoding that syndrome, what we need to do? We need to identify the syndrome. So how we are going to identify the syndrome? By adding syndrome column to the bits. By adding syndrome column to the bits, we have to identify the syndrome. And then next, determine the corresponding Coset leader. From this diagram only. We need to identify the corresponding Coset leader. After that, we need to find the error vector E. After finding this error vector E, finally we have to subtract the error vector from the received word. So this is the received word, and from this received word we are going to subtract this error vector to get the correct code word. So this is the way we can understand the syndrome decoding process. So up to now we have discussed that what a syndrome and a syndrome decoding. So syndrome is nothing but symptoms of the errors will occur, and which contains the group and the group elements. That group is nothing but, you can say that all that group cosets, and you can have that members of group is nothing but Coset members. So among those all the group members, Coset members, we are going to find one Coset leader. So to decoding that syndrome, we have to choose that syndrome column, we have to choose that Coset leader, and we have to choose that error vector. So after choosing all these ones, we have to subtract the error vector from the received word to get your code word. So that is the formation Y equals to V minus E. So among these two slides, we have to identify those two things. One is the formation of syndrome S equals to VH transpose, and to decoding the syndrome, we have to identify the errors, we have to identify the Coset leader, and the Y equals to V minus E, the form. The formation. So this is the way you can understand the syndrome decoding. So we'll see some examples regarding this linear independence and Coset independence and all. So we'll see. So this linear independence. So it is asking you to, is it true that if X, Y, Z are linearly independent vectors over Galois field of Q elements, then so are X plus Y, Y plus Z and X plus Z. Is that these are all having the linear independent vectors over this GF of Q? We need to prove that. So to prove that, we need to understand, first of all, we need to understand the Galois field. So Galois field of order M. So that we need to identify it first. So after that, what we need to do? See here, the vectors are not linearly independent over fields of character 2. The vectors are not linearly independent. So because the linear codes are over Galois field is nothing but to get the representation H equals to IRP. So we need to get this representation, right? Since GF of order 2 power M we need to write it as x plus y plus z plus x. These three things they are given, right? So we need to reconstruct this entire statement as x plus x plus y plus y plus z. So that is nothing but x plus x equals to 0 and y plus y equals to 0 because they are linearly independent vectors, right? So they are linearly independent vectors. So x plus x equals to 0 and y plus y equals to 0 and z plus z equals to 0. So we can substitute these all the zeros here. 0 plus 0 plus 0 that equals to 0. 0 plus 0 plus 0 that equals to 0. On the other hand, when q is added as a odd number, it is added as a odd number, and x comma y comma z can be expressed as linear combination of three vectors, linear combinations of the three vectors, so which therefore a span of a subspace of dimension 3. So dimension 3 is nothing but these all are the three dimensions. So 1, 2, 3 dimensions. So that is nothing but we'll take an example like, so x equals to 2 inverse of x plus y plus z plus x minus y plus z. So they are not linearly independent, so that each and every subspace is not dependent on either. So that will say that, so yes, is it true for all x and y and z are linearly independent vectors over Galois field of order q? So here the order is will taken as a 3. So 2 power 3 is nothing but obviously 8. So that will finalize this statement as a true, that 3x and y and z are linearly independent vectors over Galois field of order 3. So that is why that is the way we have to say that it is a true, right? And we'll see one more example for this different generator matrix. So here the given problem is what? Let C be a binary code with the 5, 3 matrix. So 5 rows you can have and 3 columns you can have. So 5, 3 code with the generator matrix. So what we need to do here, reduce the generator matrix to standard form 1, and second one is find the parity check matrix C, and last write out the elements of dual code C. So see here. So first one is what? Reduce the G to standard form. Reduce the G. G means generator matrix which contains number of rows and columns, and that generator matrix generates different code words. But here you will give like reduce the generator matrix to standard form. So how we'll see here. So we already discussed that to get the standard form or to get the simple systematic form of the generator matrix, what we need to get? We need to get like this formation. So I represents 1 0 0 0 1 0 0 0 1 matrix, identity matrix, and other P you can represent 0 1 2 or something. You have to get. So if it wants to become a systematic form or standard form, it should be follow this G equals to IRP. So we need to get that formation. So for that, what we need to do? We need to take this all the elements from the G. After taking all these elements in the G, what we need to do? We need to interchange the rows or columns. of the matrix. Why means we need to get the generator matrix into standard form. So to achieve the standard form or to achieve the systematic form, we need to obtain the elements into this formation. So to make that formation, what we need to do is we need to change the inter columns or inter rows. So see here how they are changing. So from this to this one, how we are changing? See here. So this 1 0 is replaced as first place. 100 is, that means R3 is replaced as 1, and second one, this second R2 is also having the same place. R2 is having the same place, and then next R1 is having the third place. R1 is going to be third place, and next R4 is going to be, R4 is also going to be the third place, same. R4 is also going to be same third place, and R5 is also having the same place as R5. R5 is having the same place. So totally three places or three places we have changed. So the rows R1, R2 and R3 will be changed here, right? And similarly, after getting this form, we need to check whether it is an I or P form or not. Still it is not in the I or P form. So what we need to do again interchanging the elements as rows and columns. So from this, what we need to do, see here. So the first one is same, and second one is going to be replaced in the third position. Second one is going to be last position. So second row is going to be replaced in the last position, and third position 110 is replaced in same as third position, and fourth position 100 is having the same position, and last fifth position 001 is replaced for this second position, replacing with for this second position. So after having this form, can we see here whether it is in I or P form or not? Still it is not in I or P form. So again what we need to do, we need to change one more row and column. So see here, this R1 is 100 is having same, okay, that it not changed, and the second one R2 is also having the same, that would not be changed, and third one is 110 is going to be changed in the 110 is going to be changed, but it is not be replaced as 110, and similarly 010 is going to be replaced. So and 100 is going to be having the same place, and last 111 is going to be changed. So that means this 0 is going to be replaced with 1 form. So to obtain this all the I or P form, so finally we achieved this. This is the I form, and this is the part is P form. So to achieving this I or P form, we need to remind these 2 points. One is changing rows with rows, and changing columns with columns. So changing of rows and columns is important to make the matrix into standard form. So to achieve this standard form or systematic form from the generator matrix, we need to recall this statement I or P. So after achieving this form, so this is the I or P form. So 100, 010 and 001, and here the whatever the matrix is presented, that is nothing but a P matrix, that is parity matrix. So finally we achieved this I or P form. So now we can say that this formation is the standard form of the generator matrix. Standard form of the generator matrix, right? And the second one is what? Find a parity check matrix for C. So this is the C code word, and to this C code word, what we need to do, we need to identify the parity check matrix for C. So to achieving this one, what we need to do, see here. So we need to change the columns as rows and rows as the columns. So from this matrix, from this 1 1 0 1 and 0 1, from this matrix we are going to change this is A, and after applying A transpose to this one, it will become like 100 and 111, 100 and 111. So for this we are going to add this I matrix. So 1001. Now it is in, this is the parity check matrix. So to get the parity check matrix, what we need to do, we need to write ARI form, or else you can write PRI form. That P is nothing but this one. So you can write P transpose and I. So that is nothing but parity check matrix. And from this standard form of the matrix and the parity check matrix, and we need to write out the elements of dual core of C. Write out the elements of the dual code of C. The elements of C are linear combination of the rows of H. So write out the elements of dual code. So dual code symbol is represented as this one. So normal code words is this one, and the dual code of the elements is this one. So to achieve this one, what we need to do? First of all, we need to identify these vectors 0 and so how many of the elements are in this G matrix? So total 5 elements are there, right? 1, 2, 3, 5, 4, 5. So we need to write the decodes. We need to write the dual codes of the code words are. So 5 zeros one time you can write, and 1 0 0 1 1 0 1 0 0 1 0 you can write, and 1 0 1 you can write, and 0 1 1 1 1 you can write. So like the way you can write different types of code words, dual code words you can write. So that is the way you can understand this dual code. And parity check matrix from the generator matrix, and the generator matrix is going to be simplified as standard form. So like the way you can understand one problem. We'll see another problems, different problems. So see here, let C1 and C2, are to be the linear codes over Galois field. Show that C equals to C1 or C2 belongs to that C1 belongs to C1 coset and C2 belongs to C2 coset, where this concatenation symbol represents concatenation of the two codes is a linear code with D equals to minimum of D1 comma D2. So that means we have to identify that C1 and C2 are linear codes, and this we need to find out the minimum of D1 and D2. So see here how we are going to find this. So we first show that the C is a linear code. We need to first show that C is the linear code. C contains a coset leader and that contains elements, and it is a linear code. See here, let x comma y belongs to C. And that alpha comma beta belongs to finite field or Galois field with order q. So that we can written as we have to show that a alpha x plus beta y belongs to the same group C. So this is one group from field q, and this is one group from the coset C. So the two elements are going to be the same group or same coset. We need to show that. So see how we are going to show that. So we show that alpha x plus beta y belongs to the C. See here, from the definition of C, colon x equals to x1 or x2, and similarly y equals to y1 or y2. So where this x1 and x2 or x1 and y1 belongs to C1 group, and this x2 and y2 belongs to C2 group. This is the C2 group. So that means x1 comma y1 vectors from this group is going to be one group, and x2 comma y2 vectors are going to be C2 group, right? So now we need to write alpha x plus beta y. We need to show out alpha x plus beta y belongs to the same group or same coset. We need to show that, right? So for that, what we need to see here, alpha x plus beta y equals to alpha of x belongs to this x1 or x2. You can take any of them, right? So we are not going to write only one x1 or only x2. We can write both x1 or x2 because of x having, right? So we can write both x1 and x2. And similarly plus beta of y. So beta of y means y1 or y2 you can write. So from those two statements we can simplify it as, we can elaborate it as alpha x1 plus beta y1 or alpha x2 plus beta y2, alpha x1 plus beta y1 or alpha x2 plus beta y2. So whereby the linearity of the C1 and C2. So linearity of the C1 and C2, alpha x1 plus beta y1 belongs to C1 group, right? So alpha x1. So here we mentioned that, right? X1 and y1 belongs to C1. So that we conclude here alpha x1 plus beta y1 belongs to C1 and alpha x2 plus beta x2 or y2. So that means x2 and y2 belongs to the C2 group, right? So here alpha x2 plus beta y2 belongs to C2 and therefore alpha x plus beta y belongs to C group. Alpha x plus beta y belongs to C group. Now we have shown this alpha and alpha x plus beta y belongs to the same group, that is C. Now what we need to show that D equals to minimum of D1 comma D2. Minimum of D1 comma D2. Since every code word in C is concatenation of a code word form C1 and C2, right? So after concatenation of C1 and C2, the elements of C1 and the elements of C2 belongs to same group, right? Same group, that is same group. But the elements of C1 can have the minimum and C2 have the maximum, or else C1 have the maximum or C2 have the maximum. So it is clear that you can write D less than or equals to D greater than or equals to minimum of D1 comma D2. Minimum of D1 comma D2, or you can say that D1 less than or equal to D2. So among those two elements, one is minimum or one is maximum, or else you can write one is minimum or one is maximum, or else you can write those two are equal, less than or equal, so you can write. So the code word C1 and C2 of 0, where C1 belongs to C1, and that means C1 is the element belongs to the coset C1, such that with respect to the C1 equals to D1 and 0 is the all 0 code word in C2. So that has the weight D1 and therefore the minimum is D1 comma D2, or you can say that D equals to minimum of D1 comma D2, or equals to, or you can write equals of D1 comma D2. So both D1 comma D2 is either minimum or maximum, or equal of D1 comma D2, either both two values are equal in that coset. So finally we shown that the linear code with D equals to minimum of D1 comma D2, or D equals to equals of D1 comma D2. So from this linear codes we are done to show like this one. Okay, right? So that is about this problem, and we'll see another problem. So perfect codes. Right? Show that binary repetition code of length n with n odd is perfect. How many errors does it correct? So we have the code with the length, and we have that odd numbers are odd, and whether it is the perfect. If it is perfect, how many errors does it correct? So perfect codes. So perfect codes are nothing but they are identifying the errors and they are going to correct that errors with the prime numbers or with the odd numbers, right? So that codes are nothing but perfect codes, you can say that, right? So we'll see how they are going to be correct. See here. So C equals to, will take as C is the code word, and that code words are nothing but A0 equals to 000 up to 0, and A1 equals to 111 up to 1. You can write anything. You can write 000, 010, 000 up to that 0. You can write anything. And similarly for the A1 also, you can write 111, 101, 110 up to last digit is 1, right? So you can take that code words. And B of length n, that means they can have some certain 3 words or 4 words or 6 words, right? So length n, we can have it. Any vector x belongs to the finite field has t coordinates 1 and n minus t coordinates 0. So belongs to this field, the coordinates having t equals to 1, or else you can say that n minus t equals to 0. T equals to 1 or n minus t equals to 0. So d of x comma a0 equals to t, you can write, and similarly d of x comma a1 equals to n minus t, you can write. from these 2 points, you can write d of x comma a0 equals to t and d of x comma a1 equals to n minus t, right? Hence, if t is the less than n by 2, that means the length by 2, that means it is t is the half of this length, then x is uniquely decoded as a0. Then x is uniquely decoded as a0. That means all zeros they will have all, or else 0 1 0 it will have, or else 1 1 0 it will have, whatever it may be. So it is uniquely decoded as a0. Whereas if t greater than n by 2, then x is uniquely decoded as a1. So that means the ending of the number is 1. So that means 0 1 1 you can take it as 1 0 1, you can take it as like the way. If it is greater than n by 2, then x is decoded as a1. If it is less than n by 2, it is decoded as a0. So a0 is nothing but ending the number is 0, and a1 is nothing but ending the number is 1. So C is a perfect, C is the code word, is perfect codes, and it corrects n by 2 equals to, it can be rewrite it as n minus 1 by 2. N by 2 equals to n minus 1 by 2. N minus 1 by 2. Right, like the way you can write. So this number of errors that will correct. So based on that a0 and a1, that means based on that bits will occur in the operation. So that ending number is 0, then it is treated as a0. Ending number is 1, then it is treated as a1. So how this much of numbers, this much of errors are corrected as with perfect codes. So about this problem we need to understand one thing, perfect codes. So perfect codes are nothing but, so that perfect codes are correcting the errors with the help of prime numbers, along with these bits, So this can also be done using the sphere packing bound. So this can also be done using the sphere packing bound. So this is the way you can understand this problem, right? And see, the next one is generator matrices and error correction. So generator matrices and error correction. So let C be a binary code 6, 3. So this is the generator matrix contains 6, 3 size of the matrix. So 1 1 0 1 0 0. So this is the 6, 3 columns. So 3 columns with the code with the parity check matrix. We'll have it. So what we need to do, find the Coset leaders and their syndromes. So to find the syndromes, what we are going to have the formula. So S equals to VH transpose, right? So with the help of this, we are going to find the syndromes. So see here, and B is the question, what to use syndrome decoding to decode the following received vectors. So 1 1 0 0 0. And second one is 0 0 0 0 1 1. So we need to decode them. How we are going to decode them? So first one is what? The code C has 8 elements. So 8 cosets. So first of all, we need to see that code can have 8 elements in the group. So find Coset leaders and their syndromes, right? So among those, we need to find the Coset values or Coset leaders. So see here, V of 6, 2. So Coset leaders are what? So all 6 means 0 0. All zeros you can write it as, and 1 with 5 zeros you can write it as, and the second one you can write it as 1, and other all. So third bit position and fourth bit position and fifth bit position and sixth bit position. After that it is moving to this first field position. So all these Coset leaders are going to be shifted like this from. So 0 0 0 0 0 0. So it means it is going to be shifted for the second position. So from this, what we are getting next one? So this 1 0 0 0 0 0. So here it is changed. And again what we need to do? We need to move the second syndrome. So that is nothing but second point. It is going to be changed. And third one 0 0 1 0 0 0. So here the third position it is going to be changed. And fourth similarly 0 0 0 1 0 0. So fourth position it is going to be changed. And similarly fifth position 0 0 0 0 1 0. So fifth position it is going to be changed. And last one 0 0 0 0 0 1. So like this, all these are all coset elements. These are all coset elements. So from these all the coset elements, the one is coset leaders. So these are all coset leaders, and the corresponding syndromes are. So corresponding syndromes are what? So first one is the 000, and the second one is 101. So 101. Third one is 110, and fourth one is 010. You can write it as so 000. The next 101, and next 110, and next 010, and next 111. So these are all the moments of these syndromes. These are all the moments of these syndromes, corresponding syndromes. So these are computed as S equals to HL transpose, where L is a coset leader. Example, the first coset leader is L equals to 1 000 000. So select the first column of H in the multiplication. HL is so 101 101. From this we are going to find this corresponding syndromes. From this we are going to find the corresponding syndromes as S equals to 101. And the next one is use syndrome decoding to decode the following received vectors. To decoding the following the received vectors. So how we are going to decode it? So use syndrome decoding. So R equals to, first one is what? 110000 110000. So to decode this one, so what is the value of S? Means 011 011. So 011. So where we can see here, 011. So the first point is 011, where 1 is replacing with this one. So the values will get 00 00 and 10 00 00 10. And the received code word is what? C equals to 1100 as common, and the one which is added in this position, that is going to be the received vector, the received syndrome decoding process. So that one is added here. And similarly for this one, so we are going to add this 010. So 010, the one is added here, and 001 000. So the one is going to be the second place, third place. So 001 and 011 001 and 011. So like the way the vector is added. So like the way by using the syndrome decoding, so to decode this following received vectors, we can decode the following vectors. So like the way we'll have this all the types of problems like a generator matrix and syndromes and syndrome vectors. So with this all, we are going to find the syndrome decoding of the vectors and finding the coset leaders and their syndromes, right? So that is all about syndrome decoding. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.